Hi everybody, this YouTube is going to be about Smith chart and that's introduction of the series 1. You also can download Smith chart from Google. Okay, this is how Smith chart look like, and there are so many applications concerning about transmission line. To get started, before we get started of the give you the idea how to use the Smith chart. I'll let's get back to transmission line so you have the better pictures. Also, what I'm going to do is I'm going to show you example how to use Smith chart first, and then come back to explain how they come up with the Smith chart and what application uh, you can use to solve transmission line problems. Well, back to transmission line from the picture here. You connect load impedance to transmission line, and the transmission line itself have characteristic impedance Z0 that you can derive from distributed parameters. I mean, in the term of R with the unit ohm per meter, L inductance per unit meter or Henry per meter, G conductor, you have the unit of Siemens per meter, and then C capacitor with the unit of farad per meter. Okay, but I'm not going to get back. You can go back to see the transmission line on my YouTube. Okay, but this one I'm going to talk about the Smith chart. Let's say even have Z0 to be 50 ohms here. The first step that we're going to take, or you want to see, is that if you want to calculate for the reflection coefficient at the load end, or tau L, you can calculate from ZL minus Z0, correct? And then what? ZL plus Z0. And you're going to end up with the magnitude of tau L, because you will get the number to be a complex number, and then the phase anchor of the transmission line. Sorry, the reflection coefficient here. Oh, it can be written in the term of the real part plus imaginary part, and I put Q as the imaginary part and P is the real part. So basically you have to deal with the complex number. You have to divide complex number by complex number. You can use your calculator and you can calculate to get the final number of reflection coefficient tau L. And then again, for the tau L plane or any complex number plane, you can see the picture like this one. You have the real part here, and then you have the imaginary part here. You take a look at tau L equal to P plus JQ. This is going to be P, and this is going to be Q, right? Imaginary part. And you can draw a line as the vector of your reflection coefficient with the phase anchor to be theta. It's from here. You measure in the direction counterclockwise. Whenever it's down here, when you measure in the direction of clockwise, your theta is going to be negative. Okay, so this is your back to transmission line pictures before you move to Smith chart. This is how Smith chart look like. There are so many numbers on the chart, but I will explain you later on, what these numbers are about. Or let's get back to transmission line. As I mentioned before, if I have a transmission line with characteristic impedance Z0 to be 50 ohms, and then I have the load impedance connect to the transmission line ZL become 100 plus J 50 ohms. What we're looking for is we're looking for tau L, or the reflection coefficient at the load N. Okay, so you're looking for tau L here. You calculate from these two numbers only. Now how to use the Smith chart to calculate for tau L. This is what we're going to do here. Okay, first of all, we're going to define ZL. When you put a cap on here, we will call this one as the normalized load impedance. It means that you don't care about what Z0 is going to be. So you're going to divide ZL by Z0, and that's what we call our normalized load impedance. In this term, you have normalized load impedance to be 100 plus J50 divided by 50, so you end up with 2 plus 1 J, or J1, and thus we're going to plot ZL on the Smith chart, and this one will lead to your tau L. So these two numbers are related to each other. Instead of you calculate tau L by equal to ZL minus Z0 over ZL plus Z0. Now take a look at for normalized load impedance, you have the real part to be 2, and then you have imaginary part to be 1. How are you going to plot ZL normalized on the Smith chart? First of all, you take a look at the horizontal line here, and I would say this is the center of the Smith chart. I will use this as a reference point. Next, you take a look at the real part of normalized load impedance. It's number 2. What you take a look at is the all of circle. What I mean is, like, this is 2. So you take a look at the circle with the number 2.0 on it, which is this one. Okay, so this is the real part of the normalized load impedance. If you notice on the horizontal line here, actually it's become just like tau L or tau plane, with the real part and imaginary part. This one corresponds to the center of the Smith chart here. Next, if you notice, the you look at this circle, the largest circle or the largest diameter. You can see this is number start from 0 and then it's increasing from the left to the right. So this one becomes 0 and is 0 0.1, 0 0.2, and then this one become 10, 20, and the end this one is become infinity. So just let you know that the real part represented by the horizontal line here is actually start from 0 from the left to the right. The rightmost has infinity, and is represented by a circle. So this is a very little circle here. The diameter is almost to be 0, and actually is 0. And for this is the circle 0. It's actually become the circle. Okay, just show you. And then if I write this down to be ZL, this also can be a complex number. If I'm going to write this down to be R plus xj, this is the real part or resistance, and this is the imaginary part. It's becomes substance, or something like that. So all the circle with the number on it is represent R, or represent the real part. Okay. So next, we're going to take a look at the imaginary part of the normalized load impedance. And you notice X is going to represent by these lines here. Okay, to get better picture. As you can see here, all the line here, this represent X or imaginary part. This is 2.0, 1.8, 1.6, and you can see here it start from very large number and decreasing when you move counterclockwise along the circle. Okay, and finally it's become 0 right here, and this is 0.1, this is 0.2, and then this is also 0.1. But what the difference is, like X can be either positive number or negative number, right? Because it's imaginary part. But R resistance, you cannot, it's only become a positive number. You don't have resistance to be negative number, but you can have impedance to be your negative number. So if you take a look at the upper part of the circle, this one represents the positive number of impedance, or X become positive, or imaginary part of load impedance is become positive, and lower part here is represent the negative number. Okay, so basically again you have like ZL can be written in the form of real part plus imaginary part, and your imaginary part here can be either negative or can be either positive. Now let's get back to what we left. off, right? So you have normalized load impedance ZL become 2 plus 1J, right? Redraw all over again. So you have ZL normalized become 2 plus J1, and this is the 2.0 circle here. I would draw not very good one. Okay, not so bad. And then J equal x equal to 1. This is R plus Jx. So x become a positive 1. So you take a look at the upper part of this circle here. Where's your 1? This is your 1 because this is 1.2, this is 1.0, and it becomes 0.9. So what you do is you draw another line here until you find the intercept point between r equal to 2 and then x equal to 1. So this become your normalized load impedance, which is equal to 2 plus J. And this is, you can find tau L from here. You can write tau L as the tau magnitude of tau L multiplied by the phase angle theta, or tau L multiplied by exponential of J theta. Okay, I'm going to show you how to get theta first. This is the reference point. I call it as the reference point, or is the center of the Smith chart here. So what it's going to do, you have to draw a line here and then pass to the intercept point. It's not very good. Okay, I'll kill it. Let's do it again. Sure it's gonna, well, just let's talk about it. So your theta actually is become this angle. Okay, you start from horizontal line here and you go into direction of counterclockwise. This gives you theta. Now you have to look for phase angle. It's not so difficult because there are so many numbers on the Smith chart here. But what you can do is you look for start which one is 0 and increasing is the angle. And then if you draw a line here perpendicular to the horizontal line here, the number up there has to show you 90 degree, correct? So if you want to find the phase angle, you start looking at something. This is 20, 30, 40, 50, 60, 70. So this is 90. So this represents the phase angle, and this is start from 0. So from this one, I would say it's about 24 degree, correct? So you have theta to be 24 degree. This is just approximate because we're not really working on the Smith chart by using a ruler or something. Now you almost find your tau L. The next step is to find the magnitude of your tau L. See, I mentioned about this one. You have like ZL normalized to be 2 plus J, and you start with ZL equal to what, 100 plus J50, right? And then you have Z0 characteristic impedance to be 50 ohms. To find tau L by hand calculation, you need to follow this equation: ZL minus Z0 over ZL plus Z0. You need to deal with divide complex number by complex number. But this one, you simply plot ZL normalized on the Smith chart. You already find the phase anchor of tau L already, which is become 24 degree, because this is 20. The line is between 20 and 30, so it is cut another. So we have 5 division. Each division is like 2, right? Degree. So I have 2 divisions here, so it's become 22. Oh, sorry, 24. Now the next step is what you can do, since the tau L. Now you need to consider what is the maximum magnitude of tau L. When you're talking about a coefficient, you don't have the magnitude is greater than 1. The magnitude is going to become between 0 and 1. That's why we call coefficient. And then, or you can take a look at the equation here. This one is ZL plus Z0. It has both real part and imaginary part. So the magnitude is, just keep in mind that the magnitude of tau L is less or equal than 1. Okay, so it starts from 0. This is your magnitude of tau L. That's why we call reflection coefficient. So you see that the maximum, this is the vector of your reflection coefficient. It's actually just end up here, start from the center of the Smith chart, as end up at their intercept point between r equal to 2.0 and then x equal to 1.0. So the maximum here, what can happen is like from here to here have to be 1, right? Because this is the longest line here, or the longest vector. So what you need to do, you need to find the ratio. What about if the length of the vector here of tau L is just from here to here, but from here to here is 1? What you can do is like you can use your compass and then intercept the horizontal line here, and you can find the ratio. This is 1. So what about this? What is going to be? Of course, it has to be less than 1. But the Smith chart also come with scale. What you can do is, I will point this one out. This is the center of your Smith chart. You draw here, come down to the center of the line here, and then also this is the end. Actually, it's become 2. It's not okay. So from here to here, you see the number 1, and this is number 2. So you simply, if you were used compass, draw whatever intercept on the horizontal line, and you can draw the line down here, cut through the scale, and you know exactly this is the magnitude of your tau L is going to be what? Let's start this from 0. I will show you why this one is 0 here. And this is the maximum magnitude of the reflection coefficient. So this is instead of you take a look at the number here to be 1, you take a look at this number here to be 0, and this is become 1. Or you can just like subtract 1.5 from 1. So this one basically is become the magnitude of your reflection coefficient is going to be 0.5. Okay, so finally you have tau L. As I explained before, you know the magnitude of your tau L, and then you know the phase angle of your reflection coefficient. Finally, you can, this is how you use the Smith chart to find reflection coefficient at the load N. Again, you start from looking for normalized load impedance, which is equal to load impedance divided by characteristic impedance, and then you plot ZL on the Smith chart, which is become a real part plus imaginary part, and this one is become 2 plus J. You find the plot and you draw the line. You have 2 plus J. This is 2, and this is, where is J? This is not clear. Okay, this one better. This is 2, and then X equal to 1. This is your line 1. So this is your ZL normalized. And then you use this one as the reference points. You draw a line pass through ZL, and then you look for the phase angle. Okay, because you can put this one at 0, and you go to move the vector in the counterclockwise, and this is your 90. You have 80, you have 70 here, so you know exactly what is the phase angle B. And again, to find the length, to find the magnitude of your reflection coefficient tau L, you simply use compass and then make it intercept the horizontal line, and then you go down to the scale to measure what is the magnitude of your reflection coefficient. Okay, so this is just the start of how to use the Smith chart to find a reflection coefficient, but later on you will get more idea and get better picture. I know maybe it's difficult, for you to start, but I will show you more and more. Especially I don't have to draw any lines, sometimes show a mistake here. It's not so easy, but I have my own lecture here. That's when I will show it to you how to use the Smith chart. That's I already put on my lecture note, so it's give you better picture. Okay, let's see if we still have time here. The maximum 2 gigabyte. Now just make it simple. This one R equal to 0 here on the leftmost of the circle, and R at this position here, the real part of your normalized impedance. This is R become infinity, correct? And also for we are talking about normalized impedance, you have the real part R plus Jx, and I call this is imaginary part, represented by these lines. Okay, so this is like 0 0.1, 0 0.2, 0 0.3. Now just for simple case, if I have the open line or open circuit transmission line, that means I have ZL here equal to what? Infinity, correct? And you know by hand calculation, you know like tau L equal to ZL minus Z0 divided by ZL plus Z0. When you have ZL become infinity, you ignore Z0 because this one is much greater than Z0 and it gives you 1. How are we going to use Smith chart to find tau L and show people that hey, I got tau L become 1? Well, first of all, as I told you, you have to find the normalized load impedance. So you divide ZL over Z0. It doesn't matter, it still come out to be infinity, correct? So this is the real part, you don't have imaginary part. Where's your infinity? Because your ZL, as I told you, you can bring it in the term of R, that's the real part, plus imaginary part. Of course, this one becomes 0 and R become infinity. Where is your R infinity? I told you before, this is R equal to 0. It start increasing from the left to the right. So 0.1, 0.2, and this is your R infinity. Okay. So now what is your, this is the reference point. What we did is that you have draw a line here, go to the intercept point, which has become this one. And you know that this is give you the maximum, the magnitude of tau L. You have no surprise. The magnitude of tau L becomes 1. Because you see this one, it's come up to be like full scale here. What is the phase anchor? The phase anchor, because the points start here from 0, so you don't have the phase anchor. The phase anchor becomes 0. So you have this is 1 and multiplied by the phase anchor, 0. So it's become 1. That's why you have the reflection coefficient of the open circuit to be 1. Now take a look at the short circuit. Your tau L of your short circuit, ZL minus Z0 over ZL plus Z0, right? When you have the short circuit, you have this one to be 0, 0, and your reflection coefficient to be negative 1. How to get tau L to be negative 1 from the Smith chart here? Well, you have to find the normalized load impedance ZL equal to ZL divided by Z0, and ZL becomes 0, so ZL normalized becomes 0. Whereas this has become R plus JX, right? Where is your R? Well, your R becomes 0. I told you that R0 start from here, and X becomes 0. So the next step to draw, this is the reference point, the center of the Smith chart. You draw the vector here, or you don't have to draw at all. So the magnitude of your tau is, this is the full scale. The magnitude has become 1, right? And your tau L is the become the magnitude of tau L and the phase anchor. Now where is your phase anchor? You start here. You go to counterclockwise, come down here. How many degrees? 180 degree of pi radian. So this one tau L and 100 degree phase anchor is give you what? Negative 1, right? or your tau L like become 1 exponential j pi or 180 degree j, and this gives you a cosine pi plus j psi pi, right? Sorry, this is pi, and you multiply by 1 the magnitude of tau L. Cosine pi is become -1, psi pi becomes 0, that's why you have tau L become -1, and it's agree with hand calculation, tau L equal to -1 for the short circuit. Okay, we continue in the next YouTube. This is just show you example, and we get deep in more detail later on.